Hello? I think there's something wrong with the audio. Hello? Yeah, it's not clear. Oh, yes.
We're in now?
Yes. Awesome.
Sorry about that. Been having lots of video and audio troubles lately. The classroom wouldn't work at all. We're in the lab right now.
Okay.
Okay, so we are playing with activity 6. And it says to use pattern blocks. I'm tweaking it a little bit. What we're trying to do is build shapes kind of like these in GeoGebra. And there's kind of a side challenge we were playing with, which was trying to replicate these guys exactly. And there's a little bit in the first part of this recording about that you could check out later.
Okay.
So I'll just show you some of the shapes I've built, and then you can start playing and then ask questions as you go. So here's my GeoGebra file. Zoom back the other way. So at first, I built this equilateral triangle using, oops, I forgot to share my desktop, sorry. Where's that? Here, there, and share. Okay, here we go. All right, so first I built this equilateral triangle here by using the regular polygon tool. And I played with that only a little bit last time. For that to work, you click on 2 points anywhere you want. And then it asks how many sides you want. I'm going to say 3, and I hit OK. The order that you choose those points determines the orientation of where it throws the next point or points. So if I click on the points instead of left to right, if I go right to left and hit OK, it draws the orientation the other way.
Oh, okay.
And that takes a little getting used to. So I'm just going to undo that. So we built that one. We noticed that the fat rhombus on the page was just 2 of those equilateral triangles stuck together.
Mm-hmm.
So earlier I built an equilateral triangle here, and I built another equal triangle here just by clicking these points in opposite order.
Right.
And then what I did is I used the polygon tool to then click those points after to get a single shape on top of those 4 points. And we can use the algebra panel in GeoGebra to turn figures on and off so they don't clutter up our viewing screen.
Oh, okay.
And so we're just kind of playing around, getting used to GeoGebra. Some of the features we used last time, like the polygon tool versus the regular polygon tool, the measure an angle tool versus the build an angle of a given size tool, to play around with these shapes. the ultimate goal for project 6 is to learn about the interior angle measures of a polygon.
Okay.
And so if we look at the next page, we're trying to say, okay, if we build a triangle, a 3-sided polygon, what's the measure of the interior angle is going to be? If we have a 4-sided polygon, what does the interior sum angle measurement appear to be? So with that in mind, if I zoom back out, I've got 3 different 4-sided polygons here. So 3 different quadrilaterals, and then I had GeoGebra measure these angles here.
Yeah.
And so to do that, let's see, they're calling that angle K. Let's eliminate angle K, delete. I can measure an angle in 2 ways in GeoGebra. I can choose the first angle tool, which is just angle. And to measure that angle, I would click with that point at the center clockwise. So if I go point, 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 it tells me that angle is 135 degrees. Alternatively, if I click this line segment and that line segment, it'll measure the angle in between. And that order is important too. So, and that takes some practice. So if I click this line segment and then that one, it'll measure the angle in between. If I try to reverse the order I click on the line segments, it measures the angle the other way.
Okay,
and so yeah, so clockwise. So that takes some getting used to. So every once in a while I click things in the wrong order and I get the wrong angle or the wrong direction. But the more we play, the easier that'll become.
So when we turn in activity 6, we just turn in what, the second page of it, where we're actually putting numbers and stuff down?
Correct, yeah.
Okay.
Yes. So we're using GeoGebra to measure those angles for us, and then it's the second page that we're going to then try and summarize what we did.
Okay.
So something that's going to come out of this part is if we add up these angles here, 135 and 135 is what, 270? 45 and 45 is 90, and if we add all that up, it adds up to 360 degrees. If I look at my other skinny quadrilateral, I've got 150 and 150, which is 300, 30 and 30 is 60. It's still 360. So what we should find is that any quadrilateral we build, the interior angle sum will be 360 all the time.
Okay.
So that's one of the goals of this project, to try and figure out, given the number of sides of the polygon, can we predict the interior angle sum?
Right.
Okay, so start playing with GeoGebra, and then if you have a question, just ask.
Sir,
All right.
for pentagons?
Ah, yes.
Like that?
Okay, so you've got 2 different pentagons, or do you have 1 pentagon?
Just the one.
Okay, so what do you have for that 1 pentagon?
Well, I drew it, but I was trying to add them up to 360, but it's not.
It didn't work.
No.
No, okay, so what does it add up to? Okay, good question. Let me build a couple pentagons,
Okay.
and then we'll compare notes.
My pentagon was 150 for each angle. This angle was 150. 150.
All right, so let's
Okay.
I'm gonna go get to a new place.
How'd you figure yours out?
Well, a square is 90. No, I did it in my head.
Oh, that's duh.
Square is each angle is 90, and that triangle is on top of it. Each angle is 60.
Okay. Yeah, I got the 90 on the bottom.
Let's see, oops.
Okay.
I think I'm gonna do what Greg said. I'm gonna build.
I just did a square of the triangle on top, and then I know that all those angles are 90, and the triangles all have 60 inside of them. So then I know that that interior angle is 150. So you add them together. I'm working on the next one, which is the heptagon.
The heptagon, yeah. So the
And I'm
heptagon.
trying to do it with manipulatives online, and I'm trying to do it with these. And it's,
Yeah. So the heptagon
found
with pattern
it.
blocks is pretty tough. Oh, you found someone else?
I found this.
Oh, you
version,
found that one.
But that we don't have that. It's a 51-degree angle on the interior.
So that's a different kind of angle. I'll talk about that one shortly.
That would be the only way to, at least, either that or I'm just not smart enough to figure out how to make it out of these pattern blocks.
It takes time and trial and error to build a heptagon out of those blocks.
7 sides.
7 sides. Yeah, I find the physical ones easier than the digital ones. Yeah. I'm gonna leave that as a challenge till next week. Don't lose too much sleep over it.
How come this
This one doesn't work. So let's see, what's the question? Yeah, so when they're talking about, so by angles, they mean interior angles. And an interior angle is an angle measured from one edge to another edge. So not.
are you working on that to go too? Oh yeah.
Those don't
Good luck.
count as exterior. So I can take any of these figures like this one here, and I can cut them up in different ways. But an interior angle has to be measured from an edge to
7
an
or
edge.
something.
This guy right here is a diagonal line edge. So that's an interior angle, that's an interior angle. I can use that diagonal to bisect or dissect these angles. So all I want to know is what do those
There's
angles
6.
add up to? Well, 60 plus 60 plus 60. I want you to add them up, right? So it's talking about the sum. One 180, right? And when we were playing with triangles in the last class,
12.
that's the idea we were messing with. There's a sharper over there, yeah.
That's 12. Both sides.
Perfect.
3, 4, 5, 5. There's 7 sides. I thought
You did it?
there's 7. I thought I have an object with 7 sides, but I don't think it's a.
Okay, so let's see. We are trying to do what here?
Number 2.
Number 2. We are trying to construct a convex heptagon. So
It has to
convex.
point in.
So convex means none of the angles can be more than 180. None of the interior angles. And this figure right here has an interior angle that's definitely more than 180.
Well, that would only be 90. Right?
No, interior angle, yeah.
Oh, okay.
So the interior angle there is what, 270.
Right.
So that's too big. Yeah, so it can't fold in on itself.
But it has to be convex. It has to fold in.
No, that's concave. You made a concave. So this guy right here, that's convex. This guy right here, that's concave because it caves in on itself.
Oh, yeah, I gotcha. Okay.
Gotcha. Yeah.
Yeah.
So for example, here I can draw a con. So come here, check this out. I'm going to draw a concave pentagon. So I'm going to click
Well, the
here.
concave pentagon is the one that looks like this.
Yeah, it caves in. Yeah, so if I go, let's see, there, and then I'll come down here, and then over here, and then over there. So that's a pentagon, 1, 2, 3, 4, 5 sides, but it caves in on itself. The interior angle is this one right here, and if I measure that angle, I can see it's more than 180 degrees.
Yeah.
So this one's concave, these two pentagons are convex. Yeah, so the challenge in number 2 is to use the pattern blocks to try and build a convex heptagon or 7-gon. And it's unlikely to happen during class. So try it a few times and then feel free to give up and try it again at another day. And we'll see if someone builds one by next class.
Where's that?
Number 2, use the pattern blocks to construct a convex hexagon. So the pattern blocks are, let's see, these guys right here. So we want to be able to stick a bunch of these guys together so we get a 7-sided figure that's convex, not concave, and has exactly 7 sides.
On the outside?
Yeah, so again, back to this. So this one caves in on itself, so that's called concave. This is convex because it never caves in on itself. So all of the interior angles have to be less than 180 to be convex.
So just a regular heptagon would be convex.
A regular heptagon would be, but I'm mostly certain you can't use the pattern blocks to build a regular heptagon. You can use GeoGebra to build one, but you can't use the pattern blocks, these guys over here.
That's the challenge.
That's the challenge, yes.
You can't use the squares. The size of the squares, except for if you make it a house.
Yeah. So you got to play around there.
So the interior angle is 1660 for this.
Yeah, so 1660 means that would have 120-degree interior angles.
So it's only the angles near the middle.
So an interior angle is an angle measured between 2 adjacent edges. So for example, this edge is adjacent to that one, so the 224.12 is an interior angle.
So
If I draw a diagonal in here, so let's put a line segment in like from here to here. The angle in here would not be an interior angle because this black line is not an edge, it's a diagonal. Does that make sense?
if it's not straight, it's an interior. Maybe.
Interior angle means you measure from one edge to another adjacent edge. If you measure from an edge to a diagonal, that's just an angle, but not an interior angle.
So for like this,
Yeah, can I draw on that with my green pen? Yeah, so the interior angle here would be that one right there. Oops, my pen apparently is dying. So this whole angle would be the interior angle. So 60 plus 60, that angle would be 120.
so what makes it? I'm not sure what makes it interior.
Interior angle means you measure from one edge to the next edge. If you measure this line right there, I'm going to make that dotted. That line right there is a diagonal.
Mm-hmm.
If you measure from an edge to a diagonal, that's not an interior angle. I know it's inside the figure, but that's not what the definition of an interior angle is.
Is this an interior angle?
If it's measured from an edge to the next edge, then yes, it is.
So all of the ones on the outside would be interior.
If it's measured from edge to edge, it's interior.
Okay.
Yep.
So when it's
All right, can I distract everybody for a minute?
So it's like a tiny triangles kind of. It's a tiny. Like
You
a tiny,
can piece those triangles together to make an interior
So
angle.
it kind of looks like a tiny pointy part of a triangle.
Sure.
Trying to make sense of it. myself.
Yeah. So it's got to make, so to be an interior angle, it has to come from two edges. Edges are on the outside of the figure.
Like this.
It could be wide, could be pointy, but
It
yes.
always has to make like a kind of a triangle,
Yes,
triangle-ish.
it's always going to make an angle, which is part of a triangle.
Okay.
Yep.
So he's always going to make like the top of the triangle.
Yep.
Okay.
All right, so can you guys take a peek over here? I want to show you something. All right, so I'm going to bring up a new GeoGebra window for this. Let's blow that up. And I am going to put the grid in and zoom in just a little. Move it. So I am going to make a, let's see what sounds good. Let's make a regular pentagon. 5 sides. So in a regular pentagon, if I were to, so I have a line segment called, I could call it DE here, and I have another one I could call DC. So if I measure the angle from DE to DC, centered at D. That gives me this, oops, ooh, wow, did all of them at once. That was
Because these are
cool.
equal, so
So let's undo that.
Why wouldn't it?
One of the one. And so here I have, let's blow up the font so Debbie can see it better. Options, font size,
right.
20.
Those are,
Is that font viewable, Debbie?
Yes.
Okay. So here I have a 108 degree angle. Now I made this to be regular, so every angle is going to be 108. Now, a reminder about just terminology. Something is called an edge if it connects two adjacent vertices, right? So DE would be called an edge. I could draw a line from like A to C. That would not be called an edge because A and C are not adjacent. They're not next to each other. You with me? So, for example, A is next to B and A is next to E. So A is adjacent to E and B. It is not adjacent to D or C because they're not connected by an edge. So adjacent means right next to it. So if I draw a segment, so let's bring up the segment tool, from A to C, that line is not an edge, but it would be called a diagonal. So a diagonal is any line segment that connects two non-adjacent vertices.
even if it's not diagonal.
Okay, so you're using diagonal in like a more general sense.
Right.
In math, in geometry, diagonal is a very specific definition. It's a segment that connects two non-adjacent vertices. An edge is a segment that connects two adjacent vertices. So my edges on this particular pentagon are AB, BC, CD, DE, and EA. So this has 5 edges. AC is not an edge; it's a diagonal.
Well,
Usually when I
get the concepts of
Okay.
the edge.
so diagonal in geometry is slightly different than like the way you might. So usually when we talk about diagonals outside of geometry, people are thinking rectangle,
Right.
but a diagonal can apply to any geometric figure.
So even if it wasn't technically diagonal, it would still be called a diagonal.
Well, that's because you have this other fixed view of diagonal in your mind. But diagonal is a more
Let's say the
general
image
term
was
than that.
rotated and the line was more.
As long as it collects two non-adjacent vertices.
The line
It could
was
be vertical.
That's what I'm
It's
saying.
okay. So diagonal as opposed to vertical or horizontal. Oh yeah, right. Yeah, that's a problem.
Math language is complicated.
So I'm gonna usually when I draw diagonals, I like them to be dotted lines to kind of distinguish them from the other things. And that didn't come out very good. Let's try that one more time with a different. Let's try that one. Dashed line maybe. That's kind of visible. Now check this out. I want to go back to my other figure for a second. So here I have a point the computer's calling D1, and there's another point over here called B1. Are those 2 points adjacent? They're not adjacent, right? Agreed?
Because they're on the same
They're,
plane.
well,
Well, not-
adjacent means there's an edge connecting them. And there is not an edge connecting D1 to B1.
Because the breaks.
Now, if I connect two vertices that aren't connected by an edge, that aren't adjacent, what is that line called that connects them?
Diagonal.
It is called the diagonal. So here's another way to tell if a figure is concave versus convex. If any of the diagonals are outside the figure, it's concave. And that diagonal, crap, I didn't want to make this point,
And if they're
is
inside
definitely
the-
outside.
If they're inside the figure, then it's
If
convex.
all the diagonals are inside, it's convex. If any diagonals are outside, it's concave. That's another way to help think about concave polygons.
Okay.
Yes, let me try one more time. I messed that up. And I like mine to be dotted lines. So style, dashed, close, pointer tool. You can kind of see it. The problem is I drew it on top of a grid line, so it's hard to make out there. But the line segment connecting D1 to B1 is a diagonal. It's outside of the figure, so therefore this figure is called concave. The other way to judge concave is any interior angle is more than 100 degrees, it's concave. If it's convex, all of the angles have to be less than 180, because then it won't cave in on itself, which this one does here.
Has to be less than how much?
If it's convex, all of the interior angles have to be less than 180.
180.
Yep.
Or
Not
equal
as a
to,
sum,
or equal to
right?
8 to 180, or?
If it's equal to 180, that means two edges form a straight line, which means they're really one big edge with a point in the middle.
Well, like a triangle. All the inside angles.
Okay, no, a single angle.
Oh, okay.
Any single angle has to be less than 180.
Okay.
Any single, yeah, not the total of
Any
all the
single
sums.
angle.
Okay.
Yeah, so check this out. So I'm gonna make, so this is wild. If we make a bigger polygon, and so let's move to a new spot in my screen. So let's make like a 30gon.
30gon.
A 30gon.
Sweet.
Okay,
What
so
would
we're
that
gonna,
be called?
a 30gon.
Now-
So I'm gonna try to make a 30gon here. I'm gonna make a 30gon with sides of 1 unit. Oops, I clicked the wrong tool. Let's try it again. Regular, I'm gonna go for a regular 30gon.
Super trigon.
And so I'm gonna say, give me 30 edges, 30 vertices, same idea. And bang, there it is. It looks like what?
A circle.
It looks like a circle, right?
Mm-hmm.
It's not a circle though,
Nope.
okay? And then I think I can use the angle tool and it will tell me that each of those angles is 168 degrees. Why 168? It turns out there's a reason for that madness. Okay, so let's take this a little farther. So let's go back to it.
Is there a whole bunch of triangles?
It actually doesn't have anything to do with pi, but that's a good
Is there a lot of
hypothesis.
triangles in there?
Yeah, there's a ton of triangles in here. So Kelly was dissecting all of her figures into triangles. And this is actually a really cool idea. So if I do that back here, if I start drawing diagonals in here, I've split this pentagon into 1, 2, 3 non-overlapping triangles. I can do that for this shape over here too. I've now split this pentagon into 1, 2, 3 non-overlapping triangles.
Huh?
1 at the top, 2, and 3.
Oh, gotcha.
Right, so I've got
What
this.
if you kept going?
Well, you can't.
Oh,
Because I already, non-overlapping,
Oh, okay,
yeah,
okay.
non-overlapping, that's the key. So for example, if I take this one, which hasn't been split into any, the first triangle could be made by taking this and going to the next non-adjacent vertex. Then I go from that point to the next non-adjacent vertex. Oh, what happened? Oh, there we go. And then I'm done. I have 3 non-overlapping triangles. So it turns out no matter how you try to do it otherwise, in any pentagon, there are exactly 3 non-overlapping triangles.
Any pentagon. there's
Any pentagon.
3 triangles.
What's the interior sum of angles for any triangle?
180.
180, yes. So if you take 3 triangles, each have 180 degrees interior, what's 180 3 times?
60.
540.
540.
Thank you,
Yeah,
Debbie.
so what we're gonna find is those 3 triangles force a pentagon to have an interior angle sum of 540,
No matter what,
no matter
what it
what.
looks like.
Yeah, so I was gonna go around and start measuring each of these interior angles one by one. And what I'm gonna find is no matter how crazy they are, they're gonna add up to 540. Okay, and so let's just double check why that's happening. So I'm gonna go back to my angle measure tool. I'm gonna pick on this weird concave pentagon, excuse me. So if I measure from here to here, oops, I did the wrong direction. Control Z, let's go from here to there. That one says it's 49.25 degrees, right? So let's move you over to the side. And then I'm gonna measure this next triangle's angle. Now again, that 49.25, that is not an interior angle. I know it's inside the figure, but it's not an interior angle. An interior angle is an angle that's measured from edge to edge.
Oh.
And that black line is a diagonal, not an edge.
It's from edge to
So this
diagonal.
doesn't count
Well,
as
you
an interior angle.
That's from
Well, you'd
an
have to
edge
total
a
that with
diagonal.
the
Yeah,
other
so
one.
then I have to find the next one.
Okay.
So now I have to go to get my angle tool, and then I find this one right here. Well, wouldn't you agree that these 2 angles together
Should
are
be-
going to give me my interior angle measure?
Yes.
Yeah, this plus that is my interior angle. So when we dissect with triangles and they're non-overlapping, we've built all of the interior angles. And 180 plus 180 plus 180 is always going to be 540.
What about the third triangle?
This one right here? Yeah, it doesn't matter because we know that inside this triangle, there is 180 degrees. Inside this one, there's 180 degrees. And all of those little triangle angles build the pentagonal interior angles, right? Because this angle right here oops, get the angle tool, this angle right here, plus this angle right here. Did I get the direction right? Yeah. Those two have to add up to be that interior angle of this particular pentagon's angle. So the angle from this edge they're calling A1 to this edge called Z1.
Cool.
So 180 plus 180 plus 180, 540. 180 plus 180 plus 180, 540. So it doesn't matter what pentagon I pick on, I can always dissect it. All right, so let's go back to the worksheet. So what the hypothesis I'm coming up with is that if I have a triangle, I know it's 180 inside.
Yeah.
A quadrilateral will have how many triangles in it?
2.
2. Yeah, take any quadrilateral. Once you draw a diagonal, you've split it into 2 triangles. What's 180 plus 180?
360.
360. Weren't we finding quadrilaterals had 360 for the sum of the interior angles? So that fits. We just discovered a pentagon has 540 as the interior angle sum.
So you add 180 to each one of these? Each side gets another 180 degrees?
Yeah, once we add another triangle,
That makes sense.
we
because-
have. Doesn't that make sense
Because
now?
a line is 180 degrees.
A line
Oh,
is
yeah.
180 degrees.
Oh, yeah.
Yeah, so that kind of falls into play here. So what we're going to find is as soon as we add another side to the figure, we've added another 180 degrees to the interior sum. So there's an arithmetic pattern forming here. So let's write, I'm going to get my spreadsheet out. So let's write those numbers down. Isn't this exciting?
Yeah.
I love this. It comes together.
360, 540.
All right, so let's go to my
We're
drive.
already in here.
Yeah, so we got
720.
180 there. Any quadrilateral is going to have 2 triangles. 180 plus 180 is
Uh,
360?
Yeah.
Yeah, 360.
that's what mental math.
Yeah, some days I am not on top of my mental math. That's fine.
980.
All right, let's go with a new spreadsheet. Call
1060.
it angles.
Yeah, 0, 3, 6, 4.
Wait till we get the exterior angles. Those are mind blowing. They're so much fun. Okay, so N.
No, I got
You know,
1140.
like pretend in the ones places that for the you could figure out.
Yeah, place value.
PO chart, like PO chart
Oh.
that they use.
Okay.
I know.
Oh, yeah,
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 except for community.
1240.
All right, so let's see. Do you have a calculator nearby, Kelly?
No, I can turn on this.
Want to borrow mine?
Yep, you're right.
I've already worked them all out.
You've worked them all out. Okay, we're catching up to you. We're
I
getting
can, I
there.
think I can.
You're awesome, Debbie.
We're catching. Hang on.
I knew the formula, which kind of
Oh, you already knew the formula.
Yeah.
Oh, because we're going to derive the formula next. That's our next one. So you can help us. So let's say I got a 180, I've got a 360, and I got a 540.
Okay.
So do you guys agree that 180, 360, 540, they're all 180 apart? You remember the trick that spreadsheets like patterns that are all the same apart? So I can just highlight those 3 numbers and say, please fill that down for me. And it'll just generate all the others for me.
Yep.
Slick, huh? Can you see that font adequately, Debbie, or should I blow it up again?
It's good.
I think I got different numbers than that.
You got different numbers than
Unless we're
that.
counting wrong. We
So-
got 800 and 980. After the 720, it went to 800.
900.
We did it wrong.
Yeah, wrong.
Yeah, you
Yeah,
added
you
wrong.
missed
Yeah, you
100.
missed. You forgot the carry.
Not bad.
Yeah, because I recognize the octagon at 1080.
So, a 10 gun is an N gun.
A tengon could be called a decagon.
Okay.
So N just means whatever size you want it to be.
Okay.
And some of them have special names, like the hexagon.
I just remember dodecagon for some reason.
Dodecagon would be the 12-sided one. And an 11gon, I don't remember anything special.
1260.
So the big challenge for us is, what if we just call it N? What's the formula? And there's 2 ways to come up with that formula, at least.
Would it be like 180N?
Okay, so let's check it out. So if we guessed at 180
Oh, plus
times N, and then we tested it here, that means this one right here would be 180 times 3. But we know that's a problem because a triangle is just one 180,
Well, could
not
it be
three
plus n?
180s.
And
So plus n.
Oh.
So, well, that would be
No.
180 plus 5, which would be like 185. So that won't work. So whenever you repeatedly add, you're right. You got to have 180 times n somewhere in there. But we're off. So how do we adjust?
divide.
So let's look at a slightly different pattern. So I'm going to throw this up on the board here.
The number of angles.
So I'm going to put a column here for interior triangles, and we'll see if we can find a pattern to that. So how many triangles are in a triangle? One. Okay. How many angles are in a quadrilateral? How many non-overlapping triangles are in a quadrilateral?
3,
Two.
2.
Pentagon.
3.
3. Okay, there's a pattern here, right? Okay, now there's 4, right? Okay, so now what we need to do is get from, okay, if we have 3 sides, we have 1 triangle. 4 sides, 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. Do you see a relationship between the number of sides and the number of triangles?
Mhm.
What's the relationship?
2 apart.
They're 2 apart. Yeah, the number of triangles is always 2 less than the number of sides. So I'm going to tweak my formula. Instead of 180 times n, I'm going to try 180 times n minus 2. I take the number of sides, drop it by 2. That gives me the number of triangles inside that figure. That make sense?
Well, I'm gonna get that the triangles are the 180.
Yeah, so that's where the 180s come from. So we have to look at the number of sides, 7. How many triangles will the 7-gon have inside of it?
5.
5, according to our pattern here. So I need 5 180s.
Okay.
So starting with 7, this formula says drop it by 2. That tells you the number of triangles living within a 7-gon. Multiply by 180 because each triangle has 180 in it.
Okay.
So let's see if it works. So I'm going to just come up here. I'm going to say equals 180 times parentheses. N is my number of sides, minus 2 close parentheses. And then I'm going to fill it down and see if it matches the numbers I came up with earlier. Ah, we got it.
What's the formula?
So the formula is take the number of sides minus 2, then multiply that by 180. So you want to put that in parentheses times 180. And that's the formula to figure out the interior angle sum.
Earlier, I accidentally did 48 sides, and it got really gigantic.
48 sides, yeah, that's pretty
Or
big.
45.
Okay. All right, so we're going to diverge from this for a second. I want to
400.
consider, so we know what an interior angle is. We need to figure out what an exterior angle is because I haven't defined that yet.
Well,
And that's weird in geometry.
It's not just the minus the interior.
Okay, so yes and no.
Yeah, you just do so the total minus the interior. You know the whole total around the circle is.
So I'm going to pick,
So
let's
that would
see,
be
I'm going to
a
draw,
37.
this is the one where, yeah, so this is addressing activity 7. So I'm going to build myself here a regular, oops, is that the wrong one? No. I want a, oh yeah, that's the right one, regular pentagon. I like pentagons, they're cute. Okay, so 5 sides. So here's my regular pentagon. I'm going to zoom in on it. So we know now that an interior angle is any angle measured from one edge to the next adjacent edge. So that's an interior angle. Now, a common assumption is that an exterior angle is an angle measured on the outside between adjacent edges. And that's not true. This angle right here is not an exterior angle. So I'm just going to put a little text note here.
Okay, now you're confusing.
Not an exterior angle.
What is it then?
It's an angle on the outside of the figure from 2 adjacent edges. But it's not what is defined as an exterior angle.
So if that's not the exterior angle, then
What is? Okay. And so the question is, why would that be the exterior? So I'm going to show you what an exterior angle is. To demonstrate an exterior angle, I need to draw a ray. And remember, a ray is a line that starts at a point and then goes out through another point forever. So for example, I could go from E to D here, starting at E, going through D, and then forever. That's a ray. Okay. So imagine Gary is walking on edge E to D. So he is strolling along. So I'm going to put a point on here, right there. And I am going to call that point, let's see, object properties. We're going to call that point Gary. Okay. So here's Gary. Let's blow up the font so Debbie can see what the heck I'm doing. Okay. So I can grab Gary and I can say, Gary, let's walk along here. And Gary can walk along and he can go right on past. Oops, no, he can't. I must have put Gary on the edge as opposed to the ray. So anyway, Gary's strolling along here. And what Gary would like to do is not stroll off on the ray DE and wander off into space forever. He would like to stay on this polygon and keep walking. So the question is, if Gary is walking in this direction, through what angle must he turn to stay on the polygon?
C and D?
He must go, right, he's pointing this way. He must rotate from this line over to that line. With me? So if I just ask GeoGebra for a second, what is the angle from that ray to this line? Oops, I must have gone the wrong direction.
180, so it'll be 72.
From this ray to that ray. Oh shit, I can't get the right direction here. Okay, so let's do this. Let's put a point out here. Okay, so we want to measure the angle from F to D to C, because that's the angle Gary has to turn. He's facing this way. He needs to switch his body to face this way so he can keep walking. Like if I was going to program a robot to walk around this figure, that is an exterior angle. If we were to program a robot to follow the edges of any polygon, we would want to tell the robot to turn a certain angle when he got to a vertex. That angle he turns, that is the exterior angle. That is what geometers a long time ago defined to be the exterior angle. Not this guy over here, but the angle one must
Even though that
rotate.
seems fairly logical.
So Gary is an ant walking around. The angle the ant must turn through to stay on the edge, the next edge of this, is the angle I want. So let me measure that angle here. So I want to go from F to D to I keep going the wrong way. From C to D to E. One more try. I think I can get it right this time. And oh, there it is. I finally got it. It's 72 degrees. What is 72 plus 108?
180.
Yeah, so here's the cool thing. Any adjacent interior-exterior angle combination has to add up to 180 because they are making that ray. The initial direction somebody would be walking on an edge.
Well, it makes sense.
Okay. So let's take this a little farther. What do you think the angle sum of exterior angles is going to be?
Is it the same as the interior?
I don't know, let's check. So here we have 108 times 5, which we found to be 540.
Right.
What's 72 times 5? Because this guy's regular. I can just go 72 times 5 because it's regular.
740, wouldn't it? Or 540 because it's 180? Or
72 times 5.
oh,
10,
sorry.
10 times 72
Let's-
is 720, so half of
720 is 360.
350, 360.
360. Okay, let's check this out. Let's try a different figure. So I am going to make myself a,
360.
let's make a rectangle. And let's throw some rays on it. Oops, I want to go to options and say stop labeling these things.
All right, he's going to give
Too many
you
labels. So Gary starts on H
90.
and he's going to walk over through L. Then he has to rotate to get over to this next line. What's the angle of rotation?
90.
90, right? So then he turns his 90 degrees, gets to J. Turns 90 degrees, gets to G.
180, 360.
So the oops, I missed one. This one to this one. So he's going to rotate 90, 90, 90. Some of the exterior angles is
360.
isn't it kind of
Interesting. Wait a minute.
like when you're over here?
Yeah.
Because this one's gonna go out this way, so isn't this angle not getting measured at all?
So here's the thing. It doesn't. Okay. So I had a roll of tape. Where did my roll of tape go? Sorry, Debbie. I can't. Oh, how can I show Debbie? Oh, we have a webcam. I'm going to need somebody to hold the webcam up so Debbie can see what I'm doing. All right. So here we're going to get physical. Turn off the screen share. And hello. Okay. So let's see. Greg, you want to be the cameraman? All right. So I'll be right back with a roll of tape.
Danielle,
Hello.
Oh, Kelly.
Oh, somebody stole my roll of tape. It was in the classroom. We will improvise. I have sticks. Okay, so I'm going to build myself a polygon. So let's build a triangle this time because it's simple. So here's my triangle. Okay. So I am going to try and walk this triangle. Okay. So my feet are moving along. And then I have to rotate. So again, let's see, I need a stick. So I need to rotate, let's see, through this angle right here, right? So I'm going to have to spin that angle.
Okay.
Right? So that I'm spinning through the exterior angle, right? So I know this angle in here is 60. 180 minus 60 means I just rotated 180 minus 60, almost 120, 120. So I rotated 120. So then I shuffle along in this direction, and then I have to rotate again. How much did I rotate? 120 again. And then I want to get back where I started, so I'm moving along. And then I have to rotate through this angle. How far did I rotate? What's 120 plus 120 plus 120?
360.
Holy moly.
I guess I'm confused because that is the thing for the triangles, but how come the polygons isn't the same? You know, because every time you add a line,
Yeah.
you add 180. How come it's not like that when you do the outside, but it is on the inside?
That is a remarkable question. I'm going to leave that open for now. But so as we make more sides, the interior angles grow. That happens. But it turns out the sum of the exterior angles, we did it for what? A triangle now, a pentagon, and a quadrilateral. Each time the sum of the exterior angles was 360. Okay, so here's a physical reason as to why. We can go over some algebraic reasons later, but the bottom line is I started facing in this direction. I walked around and I finished in this direction.
Okay.
So watch so keep the camera just like it is right there so Debbie can see my body. See how I'm facing out that way?
Mm-hmm.
Okay, so watch how I end up facing when I do one complete trip around this figure. And I want you to tell me how much my body has spun. Okay? So will I ever face this direction again? So think about that as I'm walking around.
I think it's highly likely.
120. 120. And 120.
I did not get to see that tree again until I just got back to where I started. So that means I just spun 360 degrees.
Okay.
So it turns out as you walk around a convex polygon, this is important, the convex part, you do so, you kind of walk a circle, but on other edges.
Okay.
And you just, as you were walking, you spun one complete revolution, right? You didn't see my head do an exorcist thing and spin multiple times, right? My head spun 360 degrees. Never once did I see that tree again until I got back to where I started. And it doesn't matter whether I have 3 sides or 4 sides or 30 sides. I'm going to make one spin to travel around that figure. My body is going to rotate. The weird thing is what happens if it's concave? Then weird stuff starts happening. But we can answer that question too, it turns out. All right, but I think we're running out of time for today. Yeah, oh my. Too much fun with math. So we've gone through most of what you need for activity 6 and activity 7. So the goals here were just kind of play around with what interior, exterior angles are, play around with the GeoGebra software to try and build stuff. So we are still playing with the ideas in sections 1, 3, and 4. And I think I would still like to spend another day playing with angles and postpone section 2 longer. Is that okay? Because I think we have a lot more fun we can have with angles, and I'm in no rush here. Oh, Greg's cameraman. Hello, cameraman. Sorry. He's just standing there holding the camera. Okay. So things to do. There are some things I have not addressed yet in sections 1, 3, and 5. Like I haven't talked about alternate interior angles and alternate exterior angles, and there's a bunch of other angle categorizations once you get lines crisscrossing each other. So we'll need to talk about those. And then there's some other wild stuff going on in activity 7 with respect to concave shapes. And so we still have some stuff to tie up there. So we're going to spend at least another day playing with angles to try and tie up the materials in sections 1, 3, and 4.
Are we doing all the activities?
I listed the activities on the website, so I have to look to double check them. So activities we're doing are, oops.
We're gonna use this GeoGebra.
I would save this GeoGebra file that we worked on today. Please save that. So we did activity 3, activity 5,
3, 5,
6,
3, 5, and 6.
and 7 we just started today.
3, 5, 6,
6.
And I don't believe I assigned 8. Does anybody remember?
I circled it in my book.
Okay, so maybe I did.
I can look.
What about 9?
I did assign 9, yes, but we're not ready to do 9 yet. So I'm gonna have to double check the website.
Is there a way to just, can I just print the page out that I've done already?
In GeoGebra?
Yeah.
No, well, you can, but what the better thing to do with GeoGebra is just save the file, and then you can either just give it to me, email it to me, or put it in a Dropbox on our site.
You could, but where are you saving it to, Kelly?
Yeah, you could email it to yourself.
Well, that's not good.
If you signed into, uh-oh.
Drive somewhere.
If you use GeoGebra to do a Google sign-in, then you can save it in the cloud, which is what I do sometimes. So let's see, Math 213.
So where's the memory? Is it in here?
Yeah, it's in that little thing there. Isn't that amazing? All that memory in that little tiny thing. And they just put the plastic stuff on there as a protector, which sometimes it works all right.
It's
Sometimes it
completely
doesn't.
flat.
Activities. Okay. I assigned 3, 5, 6, 7, 8, and 9. Okay, so I did assign 8, and I think 8 is where we get into the convex stuff. Yeah, 8 has the convex angles. So we're gonna play around with stars. And
Also, online, activity 1, you had to do it by the 25th.
yeah, so I also set those that you can get back into them at any time with no password. So I was just guessing as to how long it would take to get through.
Were we also supposed to turn in the circle worksheet?
Yes, so yes, I would like to collect your circle worksheet. That is for homework. And then I've got a bunch of stuff from everybody. I'll get that posted in the grade book here this week.
And you had said that there was a video before with the microphone not working. I don't think I would be able to understand any of it, but I think I have a pretty good grasp on
Oh,
this.
I thought I had tested the microphone and it was working, but now I'm not sure, and I'm gonna have to go to YouTube to check that out. But
Yeah.
I think I reviewed everything that was relevant for you.
Okay.
for the stuff that we were doing here. So if you're playing around with activity 6 and 7 and you think you might be missing some relevant information, let me know.
Oh, yeah.
I will double. It takes a while after I close, like a half an hour after I close the session before the video becomes visible for me in YouTube.
Oh, okay.
So I'll check that out as soon as we get off later.
All right, sounds good.
All right. All right. Well, have a good weekend, Debbie. It was nice to connect with you again for a little bit.
Yes, thank you.
All right. Bye-bye.